Okay, so we're in 10.6 now, just to quickly summarize what's left, we have three sections left to cover in this course, 10.6 through 10.8. 10.6 and 10.7 are kind of like a part one, part two of the same topic. They both deal with parametric equations. In this section, 10.6, we're going to start with kind of an understanding of what parametric equations are. We're going to look primarily at what we call eliminating the parameter, which we'll get to a little ways into this, and also parametrizing rectangular equations. Those are kind of like two different directions on the same concept. 10.7 is going to focus more on the graphing of parametric equations, which we do one graphing example in this section, but we'll hit the graphing a little bit harder in the next section. Parametric equations are a really important topic in Calculus 2 and Calculus 3. You're going to get through this class and then eventually move on to Calculus 1, and you're probably not going to see anything with parametric equations in that class. Don't let this slip from your memory. There's a few topics that you're learning in this class, or Math 372 if you're taking that one, that you're not going to see in Calculus 1. That does not mean that you don't need those topics. It's just because those come up in later calculus courses. This is one such topic. So finally, 10.8 is a rather large section. It deals with vectors, which is primarily going to be of use in Calculus 3, pretty much exclusively. So let's go ahead and get into this. The idea behind parametric equations, normally when we are graphing a function, or graphing an equation that's a little bit more general, in algebra, we're oftentimes looking at equations of the form y equals f of x. They don't have to look this way. For example, when you talk about conic sections, if I have something that looks like x squared plus y squared equals 1, that's not a function, but it is an equation that has a graph, and it looks like the unit circle. But a lot of what we graph in algebra does take this form: y equals some function of x. In this case, we think of x as an independent variable and y as a dependent variable. And basically, that means x receives inputs, and then y represents the corresponding outputs for that function. Then you put that input and output together into an ordered pair, which creates a point that you can graph, and then you plot a bunch of points, and then you get a curve, right? But the idea there is that one variable depends on the other. We also can talk about graphs of the form x equals f of y, where y is the independent variable, x is the dependent variable. But in those cases, one variable takes inputs, the other variable represents outputs. The idea of parametric equations is to remove the dependence of one variable on the other, and instead have both variables depend simultaneously on a third, somewhat hidden variable that we call a parameter. So to be a little bit more specific about what I mean, parametric equations take two, in this case, are going to look like pairs of equations. In Calculus 3, you'll talk about parametric equations that have three equations in them, and you can have any number of them, but for our purposes, two equations. X equals x of t, y equals y of t. In your book, I believe they write it as x equals f of t, y equals g of t, but the point is that x and y are both functions of the same variable t. They both depend on this value t that's plugged into each one simultaneously. Then that produces an ordered pair, which we could then graph. So when you have this pair of equations for a curve, or for a line, in the example that we're going to look at, but a line is a type of curve, in mathematically speaking. We call these parametric equations, and the value t, this variable t, is called a parameter. It controls the x and y coordinates simultaneously. So let's look at an example to make this a little more concrete. For this one, this is our only graphing example in this section that we're going to bother with, and then we'll do a lot more in 10.7. We want to graph the curve that's given by the following parametric equations. X of t equals 2t minus 5, y of t equals negative t plus 3. Notice that x and y are both represented as functions of t, 2t minus 5, negative t plus 3. What we do is we plug in values for t, and we do it simultaneously in both equations at the same time. So for example, I have this table here. This is straight out of your book. if I plug a 0 in for t, here x would come out to -5, which you're seeing here. If I plug a 0 in for t in my y of t function, y comes out to 3. So this would correspond to the point -5, 3, which on this graph they don't bring it all the way out to -5, 3, but that would have been a point right here. Then you can plug in another value for t. In this table, we go from 0, we plug in integers from 0 to 4. But you can plug in whatever you want for t as long as it's in the domain of these functions here. Plug in a 1 to x of t, and you're going to end up with x equals -3. Plug in a 1 for y of t, you're going to get y equals 2. So when t is equal to 1, that corresponds to the point -3, 2. And you're seeing right here, it's in the graph that I pulled out of your book, the point here is corresponding to the value of the parameter t equals 1. And then you can see other points on this line that correspond to different rows in this table. And again, the x and the y are both determined by plugging in some value of t. Okay? So if you were to graph those points, you would see that they align themselves, and we have the graph of a line here. Now, one thing I do want to point out as well, if you pay close attention to this graph, you're going to see little arrows pointing this direction. This is an important concept, especially when you get to Calculus 3, about that it's a characteristic of parametric equations and the curves that you get from their graphs. It's called an orientation. So what we mean by orientation is when you plug in these values of t, as t increases, what direction are these points being plotted? So notice t equals 1 corresponds to this point, t equals 3 corresponds to this point. So in other words, as t increases, giving us points on this line, those points are moving this direction. Okay, so that's what we mean by orientation. It's pointing in the direction that the points are being plotted as t increases, as our parameter increases. All right, we'll focus more on the graphing, like I said, in 10.7, but now for kind of the main topic of this section, something we call eliminating the parameter. So let's suppose now that you're given parametric equations to work with. Okay? The idea behind eliminating the parameter is that x and y are both, I'm putting the wrong thing here. X and y are both thought of as functions of t, right? T is the parameter here. But because they simultaneously depend on this variable t, that implies that there's probably some relationship between x and y as well. So eliminating the parameter is the process of taking, in this case, a pair of parametric equations and combining them somehow into just a single rectangular equation or a Cartesian equation. What we mean by that is an equation that only involves x and y, and the variable t, or the parameter t, is not present anywhere. So that's why we call it eliminating the parameter, because the result won't show the parameter anywhere. To give you an example of what I mean, here's the exact same parametric equations that we used up here in this graph. And what I want to do is eliminate the parameter. Typically what this looks like is a substitution of some kind. So first thing I'm going to do is rewrite these parametric equations, but get rid of the of t in there. So I'm going to write x equals 2t minus 5, y equals -t plus 3. Now there's different ways to go about eliminating the parameter, but one very common way that we're going to use here is to choose one of the two equations that you're given and try to isolate the parameter t. So notice that's not too difficult to do here. If I added t to both sides and subtracted y from both sides, I would see that t is equal to 3 minus y. Okay. Now that I've done this, I can make a substitution for the t in the other equation. So if t is equal to 3 minus y, I can substitute 3 minus y for the t in this equation up here. So x can be written as 2 times, not t anymore, but 3 minus y minus 5. And then it would benefit us to simplify this. So if I distributed the 2, I'm going to get a 6 minus 5. That would be -1. And then I also get a -2 2y. So I get negative 2y plus 1. Okay? That says that this is essentially done here. So I've written this thing as a function of y. X is a function of y. I could have also tried to isolate the y in this equation to get an equivalent equation where I would be solving for y. So if I subtract the 1 from both sides and divide both sides by negative 2, I'm going to get y equals negative 1/2 x plus 1/2. That's what I would have there. Okay, so this is an alternative version of this. You know, one variable is isolated, the other one is like an independent variable for this function. But the point of this is that this kind of reveals what the equation is if we were to have graphed it. This is telling me that the graph of these original parametric equations up here would look like a line. This is the slope-intercept form for the equation of a line. Slope would be negative 1/2, y-intercept would be 1/2, positive 1/2. Well, that's the same thing that we graphed up here. Okay, so eliminating the parameter has a couple of benefits, but one of them is that it puts the parametric equations into a form that's a little more familiar, and we can visualize its graph more easily this way. So we're going to do a few examples of eliminating the parameter just with different types of parametric equations. So here's another example. I want to eliminate the parameter, and this time my parametric equations look like polynomials. X of t equals t squared, y of t equals 1 minus 2t to the 4th. So again, start by getting rid of the of t and just write x equals t squared, y equals 1 minus 2t to the 4th. Okay, now we said before that a common technique is to try and isolate the parameter in one or the other equation, so isolate t, and that wouldn't be that difficult to do here, but we're actually not going to isolate t completely. If I wanted to isolate the t in this top equation, then I would get t is equal to plus or minus the square root of x. That plus or minus makes things a tad more complicated, and it turns out it's not even going to matter in the end. So what I'm going to do is actually just leave this first equation as is. And I'm going to notice that this second equation can be written this way. Y equals 1 minus 2t squared squared. T squared squared is t to the 4th. But the purpose of writing it this way is I've caused a t squared to appear in this equation. And I know from this equation that t squared is equal to x. So I can substitute an x anywhere that a t squared appears. That means this can be written as y equals 1 minus 2x squared. And that's eliminating the parameter because the parameter is no longer present, and instead of two equations, I only have one, where x and y appear in this equation. Okay? We're going to do an example involving exponential functions as well, which you're going to see a few of these in this section. And I know exponential functions are a topic from algebra that we haven't really hit on in our trig class at all. But you don't need to know a whole lot about them, just some basic exponent properties. So here, we're going to start the same way that we've started in the previous examples. Rewrite this as x equals e to the negative 2t, y equals 2e to the t. Okay. What I want to do in this case, I'm not going to bother isolating t completely. Now you can do that. You would need a natural logarithm in that process, and that's not necessarily a super complicated thing, but we can make our lives a little bit easier by not solving for t completely, but instead just trying to solve for e to the t. So notice in the second equation, if I divide both sides by 2, I get y over 2 equals e to the t. Okay, so that is going to give me a substitution, not for t, but for e to the t, if I can make an e to the t appear in this other equation up here. Well, I can do that. This would be the same thing as saying x is equal to e to the t to the negative second power. Again, I'm using my power to a power property to rewrite the exponent in such a way that this expression appears somewhere in this equation. So now that I've done that, e to the t is equal to y over 2. So that allows me to use a substitution up here. Okay, so I can say x is equal to e to the, sorry, not e to the t anymore. Let me back that up. Let's come down here. X is equal to y over 2 to the negative second power. I've substituted y over 2 for the e to the t that originally appeared here. Now I'm just going to simplify this. Remember, a negative exponent, its purpose is to take the reciprocal of the base. So the reciprocal of this would be 2 over y, and then I would square that. So x can be written as 4 over y squared. Okay? Eliminated the parameter. Parameter is no longer present there. All right, let's go ahead and move on to another example. We've done 3 examples so far of eliminating the parameter. One where the two equations, the two parametric equations, were like linear equations. We did one where the two equations were polynomials, the top of this page. We just did one where the two equations were exponential. Now we're going to do one that involves logarithms. Okay. So there's more than one way of going about this. Notice that the two equations, of the two equations, only one of them involves a logarithm. So I can handle this any number of ways, but what I'm going to do is try to not do too much to the logarithm. Instead, I want to work with the other equation first. So let's write x equals log of 2t, y equals square root of t minus 1. Okay? I am going to do what we did in the first example of eliminating the parameter, which is try and isolate the parameter first. And I'm going to isolate it in the second equation because I'd like to make a substitution in the first equation. That way I'm not really messing with the log much. I'm just substituting something in for the t there. So to isolate the t, it's a two-step process. I would square both sides and then add the 1, giving me this. Y squared plus 1 equals t. Okay? Now all that's left to do is to substitute this expression for the t up here. So I get x equals log of 2 times y squared plus 1. See that substitution that I made for the t there. And it's fine that x is the dependent variable and y is the independent variable. We don't need to solve for y here. It's totally fine to have it in this form. So that one actually ended up being not that easy. The logarithms can be a little bit intimidating to people. I know in algebra, logarithms, a lot of students will find that to be one of the more challenging topics. But notice we didn't really do anything with the log itself here. I didn't need to use logarithm properties. In a different example, maybe those would help, but it was fine to just leave this thing in that form. All right. Okay, I think what I'll do is I'll save these examples for the next video, and we'll probably be able to wrap up this section in that video as well.